Hello everyone, welcome to this next question on abstract algebra. This question is from December 2015 and it is of 4.75 marks. The question says, which of the following question rings are field? Right? So out of these four, we need to tell which of these is a field. Right? For that, we must see a theorem or a result stating that any field of this kind, anything of this kind, question ring of this kind, that is a field if and only if the ideal generated by this polynomial px is a maximal ideal, and hence being a maximal ideal, the corresponding polynomial px should be irreducible polynomial over f. So we say this thing is a field if and only if the polynomial over here px, that is a irreducible polynomial. So basically, out of these four, we just need to check whether this over f3, this over z, this over q, and this over f2, that are irreducible polynomials or not. If they are irreducible polynomial, we'll conclude the corresponding quotient rings, they are the field. So let us get started for the first case. So we have this polynomial x square plus x plus 1 and the corresponding field f3x. What is this? This is a finite field having 3 elements. So the elements are 0, 1 and 2. So now this polynomial is reducible in this when say let us call this as p of x, when p of 0 is 0 or p of 1 is 0 or p of 2 is 0. So let us see what is the case. P of 0 comes out to be 1, which is not equivalent to 0 mod 3, right? Why mod 3? Because we are in f3. And p of 1, that comes out to be 1 square plus 1 plus 1, that is 3, and which is equivalent to 0 mod 3. That means when you divide this 3 by 3, you will get the remainder here as 0. So here you will get a root which is equal to 1 for this particular polynomial in f3. So that means we say this polynomial given in the first case, this is a reducible polynomial, and hence the corresponding quotient ring f3x by this ideal, that is not a field. So that is the first case. So this option is incorrect. Similarly, let us go and check for the second option. For this, we need to check the polynomial p of x given by x minus 3, that is a reducible or irreducible. Now this polynomial obviously has x is equal to 3 as a root in z. Therefore, this is also reducible polynomial, and therefore this quotient ring does not form a field. So this option is also incorrect. For the third option over here, we need to check the polynomial x square plus x plus 1. So the root for this polynomial, this is a second degree polynomial, so its roots can be calculated using the quadratic formula, which is equivalent to minus b plus minus square root of b square minus 4ac divided by 2a, right? And a is equal to b is equal to c, and they are equal to 1 in this case. Therefore, our root here comes out to be minus 1 plus minus square root 3 iota divided by 2. So now this root does not belong to q over here. Obviously, this does not belongs to q over here. That means the root for this polynomial, they are not present in the field of rationals. Hence, we can say that the corresponding polynomial, this is irreducible polynomial when we talk about this polynomial over q or qx, right? Therefore, as the polynomial is irreducible, the ideal generated by this polynomial, that is a maximal ideal, and if this is a maximal ideal according to the result, this is a field. Similarly, for the last case we have we have this f2x, and the corresponding ideal is x square plus x plus 1. So we need to check the polynomial px is equal to x square plus x plus 1. This is irreducible or reducible over f2, where what is f2? f2 is a given finite field with two elements. So the only elements are 0 and 1. So this polynomial is reducible if it has a root in f2. So for that, we only have two choices, 0 or 1. So let us substitute 0 into this polynomial. So we'll be getting 1, which is not equivalent to 0 mod 2. Why mod 2? Because now we are in f2. Therefore, this is not a root, right? So similarly, we'll check for x is equal to 1. So we'll have 1 square plus 1 plus 1, which is equal to 3. And when you divide this 3 by 2, you will get the remainder as 1 mod 2, right? So obviously, this is also not a root. If this is also not a root, in that case, we say this polynomial is irreducible over f2, and thus the corresponding quotient ring, that is a field. So this is a field, right? So option D over here is also correct. So the correct options for this question, they are option number C and option number D. Well, that is it for this video. Thank you for watching.